Right then, ladies and gentlemen, today we're going to continue looking at geometric sequences and series, and if just to take you back, so we looked at in our first lesson recognising a geometric sequence and stating its common ratio. If you remember, that's where we find the value r, which is defined as one term divided by the previous term, or it's the amount we multiply one term by to get the next term. Remember, it's multiplied by, not add. If you add, it's an arithmetic sequence, a normal sequence. Okay, in the second lesson, we worked out how to calculate the nth term of a geometric sequence. If you remember, we need to know the first term to find this. We call that a. And we use this little formula down here, which is given to us in our formula sheet. So that means un, any term, is defined as a, the first term, multiplied by r to the power of n minus 1. In today's lesson, in this one, we're going to be looking at solving problems involving growth and decay. And you'll see these are very much real-life problems, kind of questions you'll get in real life you'll need to solve. So here we've got a great example of a question involving growth and decay. Bank accounts are a perfect example of this. Now remember, after each year, the interest gets added on. So after 1 year, you've got one lot of interest, 2 years, you've got two lots of interest. So in this question, where it says we have 5 years, okay, we've had 5 lots of interest. So it's kind of not what you'd expect. You normally expect it to be like a times the common ratio to the power of 4, but in fact it's to the power of 5. So if we look at this, we have got an interest rate of 4%. Now that means after 1 year, we have the initial amount plus 4%, which means we have 104%. Now we need our common ratio. Well, our common ratio here then, our multiplier, is going to be 1.04. So after 5 years, U5 will be the initial amount, which in this case is r, multiplied by 1.04 to the power 5. Remember, it's to the power 5, not to the power 4, even though we've got 5 here. Okay. So in fact, what we have here is 10,000 equals a times 1.04 to the 5, which we can rearrange, gives us a equals 10,000 divided by 1.04 to the power 5, which if we calculate that, we get £8,219, and remember we're rounding to the nearest penny will be 0.27, 27 pence. Okay, so we round that down in that case. My advice would be always to write out the full answer. Okay, so in this case I put 0.271068, but I'm just going to round it in this case. So we have this solution here. Now for the next part, we need to work out how much this will be worth after 10 years. Well, after 10 years, it's going to be the initial amount, which is A, so it's going to be the 8219.27, and then we're going to multiply this by, now leave this in the calculator, it's much easier to do that, 1.04 to the power 10. Okay, it's 10, not 16. Okay, so we're going to have answer times 1.04 raised to the power of 10, okay, which will give us £12,166. Again, remembering we're rounding to the nearest penny, so I've got 0.52902. In this case, I'm going to leave it as 0.53. Okay, I've rounded it up. Okay, so that's what we're doing in this case. Now, if we look on, the other type of question I'll ask is where they give us a geometric sequence and then they ask us to find the first value that exceeds a certain thing, or in the case of it going down, gets below a certain value. Now what you're going to find is that logarithms will come into this, so we'll be using our knowledge from our previous topic. Now first of all, let's look at this carefully. We can see that a is 3, okay, the first term is 3, and we can spot very quickly that the common ratio is 2. So un is 3 lots of 2 to the n minus 1. So this is the equation we're going to be solving, and what we're going to be looking at basically is 3 times 2 to the n minus 1 exceeding 1 million. So let's write that out like that. Okay, well first of all we can divide by 3 to get 1 million. over 3. I'm still going to leave that as a sum like that. Now, the issue here is we've got the unknown in the power. Now, in order to solve this, we use logs. So if we take logs of both sides, now what we have on this side, log of 1 million divided by 3 is simply a calculation. It's just simply a number. But the key thing here is we can take the power down. So it now becomes n minus 1 log 2 is greater than log of 1 million over 3. So then we can divide by log 2, and that gives us n minus 1 is greater than log 1 million over 3, all divided by log 2. Now this, if we work it out, log, make sure you use your calculator effectively at this point. So we've got log of in fraction 1 million over 3, close the bracket off there, then go on to the bottom, log 2, that's gives us 18.34660607. So in this case, it's going to be that is equal to 18.35, in this case, to 2 decimal places. And then simply, n must be greater than 19.35. Therefore, the first value of n where it exceeds it must be n equals 20. That's the first value where it exceeds that value. Now, you should be able to go on to attempt exercise 7c now. Please read the questions carefully. Don't get tricked by the ones where it's money, because after 1 year you've multiplied by that value. So after 1 year the power's 1, 2 years the power's 2. And it's the same with depreciation. If it's decreased by a certain value, after 1 year it will have decreased by that value once, 2 years 2 times, and so on. So just be careful of those questions. And remember, if you've got the questions where you're trying to find the first value it exceeds or goes below a certain value, that's where you're going to use logs. So whenever the unknown is in the power, you use logs.